Okay, so we are talking about stresses in beams, and the situation is that when you can use the principle of superposition, which we can use because we have small deformations and a linear relationship between stress and strain. The total stress tensor is the stress tensor due to tension compression, plus the stress tensor due to the bending moment, plus the stress tensor due to the shear force, plus the stress tensor due to fancy T, the torque. And now we've talked about all of these, and the last one we have left is the stress due to the torque. And essentially, as we've gone from left to right, the beam restrictions have gotten more rigorous, more demanding. And that's kind of going to continue here. So now we're doing the stress due to torque. And so let's first visualize how this happens. I've done that with each of them so far. So if you have a beam, let's think of one with a circular cross section. And our coordinate system is that. And we have an internal torque. So let's say that at this end we have a torque going this way and an equal and opposite one this way. That's how you get this twisting effect. And so what this is doing is twisting this side this way and this side this way. And so what happens is, so imagine that we start with this stress element along the surface. Okay? So before you start twisting it, that's the stress element. Imagine it's infinitesimal. What's going to happen to that is this, right? And in order to get that type of deformation, you need to apply a stress this way on this side, or a traction, I guess, this way on this side, and a traction this way on this side. Okay, that's how you would make it deform that way. And so what that tells us is this a positive or a negative internal torque? Just look at the two torques that I drew.
Positive?
Positive, that's right. So this is a positive torque, fancy T, and that leads to a negative X, Y shear stress. But notice that it would be different if you move to a different part on this surface. So this is a negative XY shear stress only if you're thinking about elements in the positive z direction from the centroid. Because, okay, now I'm going to ask you to do some sort of 3D thinking here, but imagine doing this same thing on the top, you know? I'm not going to draw it because it would get sort of messy, but, you know, imagine starting with that light blue outline on the top, and then you twist it. The right edge of that square on the top would come towards us, and the, you know, the left end would go away from us. So what kind of stress would that be? Well, that would still be on the x face, but it would be in the positive z direction. Okay? And so wherever you are on the surface, that stuff all changes. And if you're not exactly this direction, not exactly up, not, you know, if you're not in one of those 4 quadrants, you get a complicated combination of those things. Okay? Like if you're at some angle.
Does it matter where you are along x?
Where you are along x, not in this case, because in this case, the internal torque is just T everywhere. But obviously it can matter depending on what your torque function is. Okay, so what are we gonna do? So I'm gonna give you a function for calculating. So we're gonna always think of this as an XY shear stress, okay? But it's not always an XY shear stress. It's different in different directions. So how are we gonna deal with that problem? What we're gonna, yeah. Well, we're gonna use a coordinate system transformation. So we're gonna always start by using a temporary coordinate system with the z-axis pointing towards the element. So we'll always start. That's not how you strat. We'll always start with a temporary coordinate system. With the positive, I'm going to call it capital Z, the positive z-axis pointing toward the element. And then use rotation matrices. Okay, so get ready for that. The beam requirements. I think the biggest gap maybe in all of these beam stress calculations between what's important in a class and what's important in practice is your understanding and memory of the beam requirements. Like, when are these calculations valid? If you just go out into the real world and start applying these formulas, you're always going to be wrong. You know, in a class, you tend to have stuff fed to you that works for what you are given, you know, but you need to remember when this stuff applies. Okay, so this only works in 2 cases, which is kind of like what we had for the shear force too. The first one is round cross sections. And the second one is thin-walled closed tubes. Let's say closed thin-walled tubes. Okay, so a closed thin-walled tube. Could be that. That wall isn't very thin, but I'm trying to emphasize that the walls don't even have to all have the same thickness. It could be that. But what it can't be is this, because it's not closed. So if we have non-zero internal tension, shear force, bending moment, and torque, what cross sections are still available? You know, each one of these are cutting out possibilities.
Just round stuff.
We can do round along the neutral axis only because of the shear force.
I lost something.
Oh, okay.
My credit card, I used to be, so it was here.
Okay.
Last report, just looking.
Okay. Yeah, feel free. Okay, around. I really thought that was a student that I hadn't seen yet this semester.
I thought it was someone walking through.
Understandable, but yeah, it was like, what's going on?
Yeah, right. It's the shortest path.
I want my credit card.
Yeah. Okay, so we can do round cross sections along the neutral axis.
Thin-walled rectangular.
Perfect. Yes. Nice. And we can do thin-walled rectangular.
That's pretty useful though.
Yeah. It is. That's actually a pretty useful design for a beam. And thin-walled rectangular is where we can do it anywhere. So, I mean, if you wanted to study as little as possible, that would be the gamble to take, you know. Only just get ready for thin-walled rectangular cross sections. Okay, so and you do these two types of cross sections differently. So I'm going to start with round cross sections. And the formula is, so I said that our temporary coordinate system, I'm going to call this capital coordinate system. So the temporary coordinate system is going to have, okay, wait. Temporary coordinate system I'm going to call X, Y, Z, capital. And it's always going to have the Z, the positive Z axis pointing at the desired spot, desired location. And with that coordinate system, tau, capital X, capital Y, is equal to negative torque times rho, I'll talk about what all these are, divided by the polar moment of inertia, a new moment of inertia, I sub p. And that's what people are going to call this thing, the polar moment of inertia. Um, so let me, this rho is the distance from the centroid to the desired location. And so if you're looking at so let's say there's your cross section. Let me try to make this all 3D like. So there's your wait, I don't want that, do I? So let's say, so here's the cross section that we're talking about. And let's say here's the desired location where we want to calculate the stress. Okay. Then we're going to always start with a coordinate system with the capital temporary coordinate system, x-axis pointing down the beam, just like the regular x-axis. But the z, the positive z-axis, goes through the desired point. And the temporary y-axis is perpendicular to that, you know, following the right-hand rule. These are perpendicular to each other. Those are perpendicular. Okay. Are you with me on that? That picture isn't super clear. I wish I would have chosen a different desired location, but so anyways, to do this calculation, we're always going to choose this temporary coordinate system. And based on this idea, in that temporary coordinate system, the stress is always going to be xy, and it's always going to follow this formula, and you can always trust that sign. And then we're going to use rotation matrices to put it in the coordinate system we want. The first thing we have to be able to calculate is the polar moment of inertia. It has an integral definition because moments are always a mathematical definition using integrals. And the definition is the integral from our inner to our outer. So this, you can use this idea for hollow stuff or solid stuff of rho squared dA. And this rho is the distance from the centroid to your infinitesimal area dA. Well, we're not going to use the integral definition. Like always with these moments of inertia, we're just going to use a formula, and these are all round, so we don't even have to deal with multiple formulas. If it's a solid circular cross section, the formula is pi r to the 4th over 2. And if it's a hollow circular cross section, the formula is pi over 2 times r outer to the 4th minus r inner to the 4th. The fact that we can do hollow circular cross sections gives us a way to to get a little glimpse at what we lose by making this thin-walled tube assumption. With any time you make an assumption of thinness, that happens in a lot of classes. It's not really like a threshold thing. It's really just how much precision you require. Precision goes down as the wall gets thicker. And often people call 10 to 1 a reasonable rule of thumb. But this gives us a way to check that assumption, because you can see this will let us, so we can check for a hollow circular cross section. We can do the calculation this way and then check our answers against what the thin-walled assumption would tell us. We can do that calculation 2 different ways and see how close they are. Okay, and so we're going to do an example like that eventually. Okay, well, let's just get into an example. I'm not even going to talk about how to do the rotation matrix. You'll just see that in the examples that we do. I think it should make perfect sense. So let's say.
So, one quick question.
Yeah.
So then, is it not dependent on the row? It's a row squared, but
That's just our dummy variable for integration.
Okay. Okay, so then it's the RDR, so it becomes what, rho cubed? Or I'm just trying to think of how you would actually do the integral.
Yeah, you would do it. Okay. You forced my hand. Let's do it. Okay, so I like integral definitions. I got to be honest.
They're growing on me.
I think the thing is, the more you do and see of them, the more you recognize that it's all about choosing your infinitesimal, whatever you're the thing you're integrating over. The integrand is the other. That's what I was going to say too, but I don't think that's it. But if you choose it wrong, you can't do it. If you choose it a little bit wrong, it's brutal. If you choose it right, a lot of times it's just super easy. So let's choose. So we're going to choose this as our dA. Okay. And I'm going to choose this because this whole thing has the same rho value. Okay. So this is our rho. And what's the area of that infinitesimally thick ring? Come on, people.
2 pi dA? Or no?
Yeah, 2 pi rho
Yeah.
times d rho. Okay, so that's how we're gonna go from integrating over a separate variable, because what we're gonna do is unlatch the ends of this, pull it out into a long skinny rectangle. The width of it is 2 pi rho. The thickness is d rho.
Oh, yeah, yeah.
And so I guess the way I drew it is for a solid. It just keeps the picture cleaner, so I'm going to do that. So now we're going to do our polar moment of inertia is equal to the integral from 0 to, let's say, capital R of rho squared times 2 pi rho d rho. And I'll pull out the 2 pi, and we get 2 rho cubed d rho. And so we got 2 pi times rho to the 4th over 2, evaluated from 0 to 2,
R?
a value. Yeah, I mean, it should be to R. Do I have something wrong here, though?
No.
2 pi.
Oh yeah, it should be rho to the 4th over 4, right? Or wait. Yeah, yeah.
Yeah, I feel like I'm missing a 2 somewhere.
Well, I think, but if it's over 4, then it becomes pi over 2,
Mm-hmm.
right? Isn't that? Yeah, because the integral of rho cubed is rho to the 4 over 4.
Over 4. So yeah, right. I mean, that's why I have that there, but.
So then you should have gotten rid of the 2 in front of the pi.
Oh, right. I did the 2 twice. Duh. Okay. Thank you. So this should be. Okay. So this is just this. This is 4. Okay. Now it makes sense. This is polar, polar, polar. Okay. So you get pi over 2 r to the 4th.
So yeah, just because it's dA doesn't mean you actually need to do a double.
Right.
Kinda
Correct.
where my mind went is like,
Oh, yeah. And all those
like
integral.
R and
Yeah.
theta or-
Usually on those integral definitions, you want to find another way to do it other than double integrals. Yeah.
Cool.
All right. Example. Okay, so here is the cross section. And let's say, do I have an angle for that? Well, let's say that the point we want is, I guess we're going to just do an easy one here. That's what I have on my notes. So let's calculate the stress at 2 spots. So this is the point A, and this is the point B. This is the centroid. Our coordinate system, our real coordinate system, as always, is y this way and z this way. But that doesn't mean that's our temporary coordinate system to start with. The radius, let's say, is 5 centimeters. And let's say, oh my God, that's a huge torque. I'm going to go smaller than that. Let's say we have a 1,000 Newton meter torque at the end. And we want to calculate the stress tensor at A and the stress tensor at B. Well, first we have to calculate the internal torque, which if you're going through the whole process, we'd first calculate the external torque at the wall, then do the cut. What we're going to come up with is just a positive value of 1,000. You with me on that? Max is definitely not with me on that. Max has left the building.
Sorry.
That's all right. I know the feeling. Okay, so well, let's do the full. So here's our reaction torque. Here's our 1,000. And so that says that, go through Newton's rotational Newton's second law along x, TR is equal to negative 1,000, right? And so now our cut, and now we have our 1,000 going that way, and our internal torque, and that says that our internal torque is positive 1,000. So we have that. Now we have to calculate the polar moment of inertia. With all these moments of inertia, it's not about the point you're looking at. It's about the entire cross-section or body or whatever. So in this case, our polar moment of inertia is pi over 2 times 0.05 to the fourth, which is 9.82 times 10 to the minus 6 meters cubed, meters, whatever that is, to the fourth. And now we have everything we need to do these two stress calculations. So for part A, so I'm going to draw it again. So if this is the point we're doing that stress calculation at, we always just want to aim our temporary z-axis toward the point we care about. So this is our temporary z. That's our temporary y. Those line up with the ones we eventually want. So in this case, we're not even going to have to use a rotation matrix. And so our tau x y in our temporary coordinate system is negative 1,000 times 0.05. That's our row vector because we're all the way at the edge, divided by I sub p. And so we got 1,000 times 0.05 divided by 9.82 times 10 to the minus 6. And we get a stress of 5.09 times 10 to the 6 pascals. our x, y, z is the same as our temporary coordinate system. So the stress tensor at this point A is 0, 5.09 times 10 to the 6, 0, 5.09 times 10 to the 6, 0, 0, zeros. So now we're going to do it in one where rho is not equal to the radius of the cross section, and the temporary coordinate system is not the same as the real coordinate system. So this time our B is halfway out. Our temporary coordinate system is this way with the z-axis pointing this way. That means that the temporary y-axis has to be down. Everyone with me on that? We've already calculated the polar moment of inertia, so all we have left here to do is just stick stuff into the calculation. So tau xy in the temporary coordinate system is negative, I left off the negative, don't do that. For part A, I don't know how I missed that, but it's important to remember that this sign, you can trust this sign in these calculations. Okay? So we have tau xy is negative 1,000 times, what's the row vector here?
0.025?
Yep, half of the radius divided by 9.82 times 10 to the minus 6. And so that's 2.55 times 10 to the 6 pascals. Negative. Okay, but now, so I'm going to write out this stress tensor, but you have to remember this is a temporary stress tensor. This is in the coordinate system that doesn't mean much to us. Okay, so the stress tensor x, y, z. Computer crash to slow us down. So this is equal to 0, negative 2.55, I'll do it in megapascals, 0, negative 2.55, 0, 0, 0, 0, 0. And now you have to think, what rotation of the coordinate system do we need to go from this to this?
180 about x.
What?
180 about x.
Yeah, that's right. 180 or negative 180. And so our rotation matrix is, so we got 1, 0, 0, zeros down the column. And then cosine of 180 is negative 1. Sine of 180 is 0. And then 0, positive 1. And so the final stress tensor at B is Q times the stress tensor in the temporary coordinate system times Q transpose. And what you get out of that is these values, in this case, just become positive. So 2.55. So 0, positive 2.55, 0, positive 2.55, 0, 0, 0, 0, 0. Any questions about that? Sometimes it takes, I mean, 180 is kind of foolproof because you can go positive or negative. Maybe it takes a little more thinking when the angles are 30 or 120 or 290 degrees or whatever, but that's the idea of what you have to do. Okay, that's all.